কি কোনো কোশ্চেন আছে?
নো স্যার।
বোঝা যাচ্ছে তো সব?
হ্যাঁ স্যার, একটু হালকা করলে বোঝা যাচ্ছে।
আচ্ছা, তাহলে অ্যাসাইনমেন্ট গুলো করে সাবমিট করো। ওকে, আচ্ছা। তো টুডে ইউ স্টার্ট ডিসকাসিং অন finite element formulation of bars. Actually, the bars are uniaxial. Recall, we had the strong form or the so-called differential equation, which went like this. With boundary conditions. And the traction boundary condition. So we are talking about this configuration here. A bar which is fixed at one of the ends and then acted on by a distributed load Q, per unit length. This one has kind of this unit, and then you are applying at the free end, you are applying this concentrated force P. So we showed that in two ways we can arrive at that equation, uh, either from the potential energy statement or by uh, using Newton's method, where we would draw the free body diagram at the boundary as well as at an arbitrary x location. So x is the coordinate along the bar, and the bar also has the following properties: Young's modulus, cross section area, and the length of the bar. Okay. Now we also had the V statement, assuming V is the variation of U, that is an arbitrary variation of U. So it should satisfy that in gamma U V equals 0 or V0 equals 0 must be satisfied. And there is no other condition on V, and V could be anything. So now we had the following expression. True for all V satisfying this essential boundary condition. Okay. Now, in finite element method, No, if you are to solve this problem from the strong form using analytical method or closed form method, so you directly integrate this quantity, integrate this equation, and even if this distributed load of yours, if that were a uniformly distributed load in reference to bar, of course, it's not a beam, but the load could be uniform, as in the per unit length, that value is a constant. Okay, you can imagine that it's hard to depict in a uniaxial problem, but imagine there is this bar, and as you move along the length, the force on the bar also, uh, per unit length, force per unit length, that also becomes more and more strong. Okay, so higher and higher value. So I'm trying to depict that with color. Okay, so that is also a possibility, but in this case we are talking about, let's say, even if we had uniformly distributed load, as you can see, by double integration you are going to get a quadratic function. So even if we think of u being a polynomial in x, that would at least be a quadratic polynomial for a non-zero q. Okay, so just keep that in mind. That is the exact solution, or in order to get an exact solution, you need uh, u of x to be at least a quadratic function, even if your distributed load is uniform. So, so the next thing that we are going to do is, uh, as a starter, you'd imagine the entire bar to be a single bar element. Okay. Now, we could also have taken multiple elements along the length, and each of these bar elements, let's say we would number, so they are bounded by, so like a geometry, a line is bounded by 2 points. The element is bounded by, one dimensional element is bounded by two nodes. Okay, so I put element number within this circle, and the node number close to the nodes. Okay, so there would be, if I were to divide the geometry with three elements, okay, then um, I would have four nodes in the mesh. uh, Also, let's say this is our element, and these are the nodes 1 and 2. Now there is a difference between this numbering and this numbering. Here we are doing a general formulation, which means these are element numbering, and these are global numbering. Point being that if you are no element number 2, node number 2 acts as node number 1, and node number 3 acts as node number 2. Okay, so what we are about to develop is a routine process which we can repeat for multiple elements, and computers are good at doing routine processes. So, so given a element, okay, say element number 1, we have two boundary nodes 1 and 2, and this one is the physical coordinate, that is x, and those are, let's say, x1 and x2. Now these are known quantities, of course. What might not be known is the deflection. Okay, we might also know that, for example, at x equals 0, u is 0. So the primary variable that we are solving for, the value of that at the two nodes are, let's say, u1 and u2. we might not know them. We might, in the end, we might want to solve for them. That's not the point. Here, we just define that the value of u at node 2 is u2. And in addition, we would define something like a natural coordinate. Now, strictly speaking, a natural coordinate is not really required in a one-dimensional problem. In a one-dimensional problem, when we move to a 2D or a 3D problem, a natural coordinate, the concept of natural coordinate is a mandatory. Okay, and actually, when we move to 2D, we need two natural coordinates, and when we move to 3D, we need three natural coordinates. But it would be a good practice for us, because that would make us habituated to have the understanding of the natural coordinate. And for that, we have the values -1 and 1. Okay. And since we are defining defining u, we would also define the values of v as v1 and v2. In the end, there are two nodes, so we have two shape functions. Okay. So there is n1 and there is n2. Now, value of n1 at node 1 must be 1, and at node 2 it must be 0. Value of n2 should be the other way around. Now, the value of the ith shape function at the jth node is something called a Kronecker delta. Okay, which means equals to 1 if I equals j, equals to 0 if I not equals to j. Okay, and that is the definition of Kronecker delta. Okay, now what does Kronecker delta belong to? Any identity matrix of any dimension is populated by Kronecker deltas. In 2D, that would look something like this. You see, 1 0 0 1. Okay, so right now we are talking about a situation when a single element has two nodes. Okay, and and we are defining the values of the shape functions at those two nodes. Okay, and that's why we have this 2 by 2 matrix. So if our element had three nodes, that is also possible. If our element had three nodes, okay, then we would have a 3 by 3 Kronecker identity matrix. Okay, in that situation. Anyways, এই পার্টটা কি সবার লেখা হয়ে গেছে? কারণ আমাকে মুছতে হবে।
স্যার রেকর্ড হচ্ছে তো, অসুবিধা নেই।
অসুবিধা নেই, তাই তো?
হ্যাঁ স্যার।
Okay. Now, how far should I delete? I need this expression, and I need whatever is still here. So, yeah, let's just delete from this portion. Okay. Now, there is one other property that must be true with the shape functions, that summation of ni at any given xi should be equal to 1. Okay. So now let's look at how everything is mapped using the shape functions. Okay, value of u at any given xi is n1 of xi times u1. Please understand, u1 is merely a coefficient. n1 is the shape function of xi, dependent on xi, that defines the functionality of u of xi. Next comes n2 of xi. This could also be written as n1, n2. It's implied that these are functions of xi times u1, u2. Also could be written as n matrix, which is 1 cross 2 times 2 cross 1 u hat. And same thing, because u and v must belong to the same function space, v being the variation, of course an arbitrary one. So v of xi, now look at this carefully, I'm writing it to be u hat transpose n transpose. Okay. Now this choice is deliberate. A dot product, you see, it's a dot product of two vectors, the n vectors and u vectors. Okay, that's how you have n1 u1 plus n2 u2. I can write it to be a dot b could be written as a transpose b or b transpose a, because same is b dot a. Okay, I hope you understand that even if you did, sorry, this one is v. So again, v hat would be the vector of v1, v2. So v hat transpose n transpose basically does v1 n1 plus v2 n2. Okay, n being a row vector. এই অবধি কি বোঝা যাচ্ছে? So all I am doing is n1 v1 plus n2 v2, of course. That is the general form, which can be shown as v1 v2 times n1 n2, and that's where this expression comes from. এই অবধি বোঝা যাচ্ছে?
একটা কোশ্চেন ছিল,
হ্যাঁ বলো।
তো বলছে এলিমেন্ট নাম্বারিং এর জাই -1 আর 1 কোত্থেকে আসছে, মানে কিভাবে মানে নেওয়া হলো ওটা?
ওটা আমার চয়েস। Xi is not really there. That's not the physical coordinate. Okay. It's not really my choice, but it could have been my choice. That's the one that I'm implying here. So it helps in formulating the expression of shape functions. I mean, I could have also taken 0 and 1
Yes.
and gone with it, but later on when we write the expressions for the shape functions, okay, that's when you'd see that -1 and 1 kind of works. Okay, মানে x is the physical coordinate, but we are going for a natural coordinate, and we would define shape functions based on that natural coordinates. Okay, এই এক্সারসাইজটা এখানে রিডান্ডেন্ট মনে হতে পারে, but when we move to two-dimensional problems, you would realize that this is mandatory. Okay. Also, when it comes to computer programming, this also could be fruitful, because then working with, because a natural coordinate has definite values -1 and 1 at the two ends. Okay, whereas these values of x1 and x2 would keep on changing. Let's say if you move on from element number 1 to element number 2, now x1 is replaced with x2 and x2 is replaced with x3. Okay, but for the natural coordinate it still is -1 and 1. বোঝা গেল? আচ্ছা, এরপরে জাস্ট একটা জিনিস বলবো, সেটা হচ্ছে যে x is now also a function of xi. The physical coordinate is also now a function of xi, and it's nothing but n times x hat, where x hat is but x1, x2. Okay, and that's where is a justification of something I wrote very sneakily, which is isoparametric element. That means the coordinate as well as the displacement or the degree of freedom, okay, they are being mapped with the same set of shape functions. You see, so all I'm trying to say here, it is, this is what it means: n1 x1 plus n2 x2. And we would see examples where that would not be true, okay, but mostly we would go with isoparametric elements where the coordinate and the displacement are mapped with the same parametric form or same set of shape functions. And when we do the beam example, you would see that is not generally true. ঠিক আছে? So these type of elements are called isoparametric elements. এই অবধি বোঝা গেছে? এই অবধি কোনো কোশ্চেন নেই তো? শোনা যাচ্ছে আওয়াজ আমার? Okay, now about the shape functions. Now you could have chosen any function, any type of functions, exponential, logarithmic, sinusoidal, as shape functions, but the simplest one we can think of are polynomials. Now what polynomial you can construct, let's say these n1 and n2s are polynomials, okay, and you have the value of n1 at 2 locations and value of n2 only at 2 locations, okay. So when I give you two conditions, what type of polynomial can you construct? When I give you two values, what type of polynomial can you construct? Linear, right? So n1 and n2 are linear polynomials, okay, and actually they are Lagrange polynomials. In finite element method, we typically use Lagrange polynomials. Which means n1 would be 1, which is its value at xi equals -1, okay. So xi minus xi2, again this quantity is xi1 and this quantity is xi2, divided by, I would suggest you go to internet and learn more about Lagrange polynomials. Xi1 minus xi2, okay, and then 0 times xi minus xi1, xi2 minus xi1. That is the expression for n1, okay. What does it ensure? That when you put xi equals xi1, okay, this term right here, this fraction becomes xi1 minus xi2 divided by xi1 minus xi2, which is that this fraction, the numerator and the denominator become same and it essentially becomes 1, which means you have the value of n1 at xi equals 1, which is 1. what happens to the second term? When you substitute xi1, the numerator becomes 0. So the value of the n1 at xi2 doesn't come into the picture. So Lagrange polynomial essentially gives you the simplest way to ensure that a given polynomial has so and so values at the so and so locations. Okay. So this is what, in the end, your n1 would look like. So it would be one minus xi divided by 2. And in the similar way, you can try to construct n2. You'd see n2 would be 1 plus xi divided by 2. Okay. I would say you try that on your own. So this is a small assignment. How to get n2 using Lagrange polynomial. Achha, one more thing. When the value of xi equals xi2, again, the numerator on the first term cancels out. And here it becomes xi2 minus xi1 divided by xi2 minus xi1. Essentially, this one becomes 1. And then you have value of n1 equals 0 at xi equals xi2. Okay, so this is the simplest way to ensure that the polynomial has so and so values at so and so x or xi. Now, if you compare n1 and n2, this general expression that you can write, the ith shape function is essentially 1 plus xi xi divided by 2. Now, can you see that? এই লাস্ট এক্সপ্রেশনটা এটা কি বোঝা যাচ্ছে?
Yes, sir.
Yes, sir.
Okay, so in the end, your shape functions look like this. So you see, this one is your xi coordinate, and this value is -1, and this value is 1. This green line is your n1 of xi, has a value of unity at node 1. And this red line is your n2 of xi. It is 0 at n1, but at n2, it has the same value as n1 at xi1. Also check, if I add n1 plus n2, it becomes 1 plus 1 minus xi plus xi divided by 2 equals 1, which is also important. Now, why do I need this condition, that summation of ni? It is well understood. Why do I need this form for the shape functions? Okay, that way the shape we get u at xi1 is u1, because you see it is u1 n1 plus u2 n2, but at xi1 this one is 0 and this one is 1. So this condition is pretty well understood. This condition is not so trivial. The thing is, let's say for some reason you have u1 equals u2 equals u star, then your u would be u star times n1 plus n2. Now this n1 plus n2 is still a function of xi. Okay, you see n1 is a function of xi and n2 is a function of xi. Okay. Had this condition not been trivially true, you would see somewhere between 1 and 2 u having a value other than this. If this condition is not met, trivially everywhere from anywhere between 1 and 2, having the value of u same at the two boundaries of the element or two nodes of the element would not be able to ensure that throughout it is the same value. Okay. Then to account for that variation, okay, we need to look for any other degree of freedom. Okay. বুঝতে পারছো কি বলতে চাইছি এখানে? Currently, with this summation to be true, that summation ni equals 1, what we can ensure that if by solution we get in u1 equals u2, okay, that means that bar element is having a rigid body motion. Okay. That means this could be a problem in dynamics as well, where the bar is experiencing a rigid body motion. Okay. But if that condition was not met, u1 equals u2 could also mean that somewhere between 1 and 2 there is this variation of u. Imagine if n1 plus n2 were something, okay, which would be for example, if you see, if I do this, if I add this quantity to n1, n1 still satisfies the condition, or if I do the same thing to n2, so they still satisfy that one of the, because this quantity is 0 whether you are at -1 and 1, so they still satisfy the condition that n1 equals 1 at node 1 and n1 equals 0 at node 2 and vice versa. Okay. But then you would not be able to ensure that their sum is trivially 0. So that means even with u1 equals u2, you would have some sort of variation of u along the geometry. Okay. And that is not allowed. Okay. Because then you do not have the access to account for that variation. For instance, when xi equals 0, this need not be 0. And if I take, if I add the term only over here, so then I would have a value other than u star at xi equals 0 and other places also. Okay. So that is not allowed. Okay. So let's now move into the solution. Now we have seen the variational. Achha, what more do we need? We need to express strain. Strain is but u prime, which is du dx, which could be written as du d xi dx. Now, what is dx d xi? Remember, this one is x1 times n1, which is 1 minus xi divided by 2, plus x2 times n2, which is 1 plus xi divided by 2. Sorry. This is what x is. Okay. Now, can you get dx d xi from here? dx d xi কত হচ্ছে একটু বলো তো? dx dxi is referred to as the Jacobian, okay, which in 1D is a scalar. And when we move to 2D, we would say it's a 2 by 2 matrix. So when we move to 3D, it is going to be a 3 by 3 matrix. এটা ক্যালকুলেট করা যাচ্ছে dx dxi? কি কিছুই করা যাচ্ছে না? না আমার কথা শোনা যাচ্ছে না? হ্যাঁ, তোমার কথা কিছু শুনতে পাচ্ছি না সুমিত। হ্যাঁ, না একদমই শোনা যাচ্ছে না কথা। বাকিরা কি কেউ কিছু করছো না?
স্যার ডিএক্স ডিজাইটা তো স্যার এখান থেকে মাইনাস অফ এক্স হবে, মাইনাস অফ এক্স বাই টু, মানে মাইনাস অফ এক্স ওয়ান বাই টু, কারণ এখানে স্যার ওয়ান মাইনাস জাইট ডিভাইডেড বাই টু আছে, তার মানে হিসাব মতো যদি আমরা দেখি তাহলে ওটাই ডিফারেন্সিয়েশন হবে একমাত্র, আর এদিকে আরেকটা ডিফারেন্সিয়েশন হবে, তার মানে স্যার মাইনাস এক্স ওয়ান বাই টু প্লাস এক্স টু বাই টু।
এইটা করতে 10 মিনিট লেগে গেল। x2 minus x1 you refer to as the length of the element.
Yes sir.
So 2 divided by LE du dxi. Now that would be 2 divided by LE del n1 del xi del n2 del xi times u hat. Okay, you do understand that u1 and u2 aren't a cut silent nego. u1 and u2 are not functions of xi. So you don't take derivative of those quantities. Instead, you take derivative of the shape functions. Now, in the end, you have the expression for strain, which is 2 by LE del n1 del xi. In this case, it would look something like, what would be del n1 del xi? How much is del n1 del xi? This thing is n1. What is the first derivative? What is the derivative with respect to xi? And this thing is n2.
minus 1 by 2.
So there is minus half and plus half
Yeah.
times u hat. Can you simplify it further? If you really think about it, this is telling you this is u2 minus u1 divided by x2 minus x1. Indeed, if u changes linearly along the length, if u changes linearly along the coordinate, that's what is assumed. You see, x is a linear function of xi and u is a linear function of xi, which means u is a linear function of x. And if indeed the quantity changes linearly, okay, then so-called strain, which would be u prime, it is everywhere. Let's say this one is x1 and this one is x2 and this one is u2 and this one is u1. It is always u2 minus u1 divided by x2 minus x1. Okay. Now, I'm not going for the final expression, but just before that, I would refer to that as being the B matrix, which is 1 cross 2 times U hat. And similarly, I would get the variation of the strain, which would be V hat transpose B transpose. Okay. So what is V hat? If you have not remembered it, it is V1, V2. Now we can write the variational statement that we had written earlier for the entire bar 0 to L. So this epsilon V here is basically V prime. So you have E times A times U prime times V prime, right? So V prime is V hat transpose B transpose, and U prime is B times U hat dx equals 0 to L Q times V, which we would write as V hat transpose N transpose times Q as a function of xi dx plus P times V hat transpose N transpose, but N transpose evaluated at x equal L. In the end, from this entire expression, we can take V hat transpose to be common. Achha, by the way, we need to mention that this is true for all V1, V2. Okay. Now, please understand what just happened with this statement right here. We had a definite a problem given in definite integral, and we had a function to solve, and the variation to that function was another function, another arbitrary function, which would satisfy the essential boundary condition. Currently, our goal is to find out the displacements u1 and u2. Just two numbers, two coefficients, not functions. Because we have already made up our mind on the functional form. And this is the functional form. U equals n1 u1 plus n2 u2. We have already decided that the function is piecewise linear. That means if this is u and this is x, and let's say this much is element number 1, and this much is element number 2, and this much is element number 3, then from node to node, this is how u changes. This is how u is allowed to change. So that's what we have made up our mind. Okay. And if there are more nodes involved, okay, between 0 and L, so you can put V3, V4, etc. So now we are not looking about the arbitrariness of the V as a function, but the values of V1, V2, V3, V4, etc. Okay, which is the arbitrariness of a set of values, set of numbers. Okay, going from solving a function with arbitrariness of another function that we would never solve. We are going into identifying some numbers, some coefficients, okay, using the arbitrariness of another set of numbers or coefficients, which now is a variation. And then think of this in another way. Currently, we are trying to solve for this vector u hat using the arbitrariness of another vector v hat. The earlier problem involved solving a function with the arbitrariness of another function. Now we are solving for a vector using the arbitrariness of another vector. And we have said this in this class and repeatedly, that functions are essentially infinite dimensional vectors. Okay. And by approximating a function in some way, for example, in a piecewise linear fashion, we are able to represent the function in finite dimensional space. For example, in two-dimensional space. Okay. With the values u1 and u2. Okay. The function being an infinite dimensional vector, we are not able to represent that when we are, including all possible set of all possible functions. But if we limit our set of functions into a smaller dimension, okay, then we are able to represent that as vectors. Okay, so essentially the problem which was initially solving a differential equation, and then it become solving the function from a definite integral, now it has become solving a set of algebraic equations. Okay. Now if I take v hat transpose common from this expression, so this is what I get: 0 to L EA B transpose B dx. Please remember, v hat is only a set of coefficients v1, v2, which are not functions of x. Neither are they functions of xi. Achha, by the way, I would also change the limit from -1 to 1, and the dx would be now j times d xi. This j, of course, is LE divided by 2. You see, we defined dx d xi, right? So the integration must be done in natural coordinates. Then comes another term, -1 to 1, n transpose q of xi, LE divided by 2 d xi, and then comes another negative term, p times n transpose evaluated at x equal L. Okay. So again, this is essentially a dot product. You take V1 and then multiply with that the first row. Achha, before going there, achha, one more thing I missed, that was to introduce u hat over here. Now, আচ্ছা এই অবধি কি বোঝা গেছে যা বলেছি?
স্যার
হ্যাঁ বলো।
হ্যাঁ স্যার, ভি প্রাইম ইজ ইকুয়াল টু, এটা কি স্ট্রেইন ইনটু ভি, এটা মানে ব্যাপারটা বুঝতে পারলাম না। ভি প্রাইম ইজ ইকুয়াল,
You can say call it variation of strain. Essentially, it's a mathematical term. No physical significance. কোনো মাথা মুন্ডু নেই physically. Okay.
Okay.
So you see, in the weak form involves the symmetric bilinear form, half AUV,
Hmm. Hmm.
which basically means we treat V the same way we did U. বোঝা গেল?
Okay.
But therefore, we would encounter terms which looks similar to the terms corresponding to U. If you have U prime, then you also have V prime. And you don't have to call it anything. I'm just calling it variation of string. Okay. And representing it as epsilon of V. But it is
Okay.
nothing. It's just a mathematical term because that's how the weak form turns out to be. Okay. আচ্ছা, এই অবধি যদি বোঝা গিয়ে থাকে আমরা আরেকটু করি, হ্যাঁ? So you do understand that u hat and v hat are not functions of x, and they very easily come out of the integration all the time. Now what you would do is, okay, we would perform this integration, j being le by 2. Then we had the expression for b's, right? So can you do this integration? Of course, e times a times le divided by 2 comes out of the integration. So B transpose is actually 2 cross 1, and B is 1 cross 2. So when you do this multiplication, this type of product is called a dyadic product. So we learned A dot B is A transpose B, which is a dot product. Then A dyadic B would be A B transpose. Okay. And therefore, A dyadic B would be a matrix, and the ijth component of that would be AI Bj. এগুলোকে লিখে লিখে করো. How would B transpose look like? Given B is something like this. What is the expression for B? B এর এক্সপ্রেশনটা কি?
minus half half.
আবার half.
Oh.
Then write the expression for B transpose. B transpose B মাল্টিপ্লিকেশনটা করা গেছে?
হ্যাঁ স্যার।
কত এসছে?
1 -1, -1, 1.
Okay. And did you notice that each of these components, okay, আচ্ছা একটা জিনিস বলে দিই, when you are differentiating or integrating a matrix with respect to a scalar, that essentially means you do the integration or differentiation of each and every term in that matrix. বোঝা গেল কি বলতে চাইছি? So basically here we are doing 4 integrations of each individual term. Okay.
Okay. Okay.
Okay. Then look at any of the terms here. All of these are, so if I were to write terms like terms involving xi to the power 0, xi to the power 1, xi to the power 2, etc. There are no terms involving xi to the power 2 or xi to the power 1 or anything. So these are all xi to the power 0. Okay. Now xi to the power 0, xi to the power 2, each of these are even functions. And xi to the power 1, if those terms were there, those would be odd functions. Now, if you have even functions involved in an integration from -1 to 1, that is an integration from 0 to 1 twice over. Okay. Now do this integration. And this one we would call the element stiffness matrix of the bar element. Okay. And if you have not noticed it carefully, then the stiffness matrix for a spring essentially looks like this: K minus K minus K K. We had done this, few classes before, which essentially means K in this case is equivalent to EA divided by LE. Which means if the delta U, the change in length, is del U, then you divide that by LE, that gives you strain. Multiply that Young's modulus, that gives you stress. Multiply with the area, gives you the force. Will tell you how much force is involved. So this one is consistent. Okay, but this one is only true. This one is only true when you are dealing with a linear bar. If the bar has only linear change in deflection, that means gradually from fixed end to free end. Okay, so then only this one is true. Then only it would be like a linear system. Okay, or rather, sorry, then only it would be the stiffness matrix would look like this. Acha. The bar, of course, is linear because it's elastic and everything is there, but it's the the involved distributed load that might change how the deflection occurs. That need not be occurring gradually. Okay, so we have this element stiffness matrix for the bar, and then we have this V hat transpose, an arbitrary V hat transpose. Now, can you perform this integration -1 to 1 N transpose For the sake of simplicity, assume the distributed load is uniform, LE by 2 dxi. Can you perform this integration? So for the sake of simplicity, consider Q0, assume Q of x is just Q0, a constant, uniformly distributed load. Okay, assume that condition. Now for n transpose, you'll have to write down the expressions of n1 and n2, which is, so you can directly take Q0 LE divided by 2 outside of the integration. And here you have 1 minus xi divided by 2 and 1 plus xi divided by 2. Then you are integrating with respect to dxi. And notice again one thing, that this one is xi to the power 0 and this one is xi to the power 1. Even function, odd function. So what happens to an even function when integrated between a negative limit to the same positive limit? It's just the integration from 0 to 1 twice. But what happens to the odd function? Once you integrate an odd function like this one, the positive and the negative area cancel out, which basically means for the odd function, it would simply be 0. So in the end, you have the following expression, Q0 LE divided by 2, then 1 and 1. Now, if you add these two quantities, so the two terms of the vector, it becomes Q0 times LE. That is the total distributed load on the bar. So that has been equally divided at the two nodes. So in the end, you have the stiffness matrix times U hat minus, this one we would call the force vector due to the distributed load minus FQ and then the next term is P times, now this N matrix, rather N transpose matrix, which is 1 minus xi divided by 2 and 1 plus xi divided by 2. Okay. Now, when you evaluate that at x equal L and considering the entire bar to be a single element, okay, can you tell me what should be the value of N transpose? If you consider the entire bar to be a single element, then x equal L, okay, would correspond to xi equals 1, right? Okay. So the value of N transpose at x equal L is essentially this quantity, 0, 1. Okay. So the third term in this system is essentially 0, P. So you applied the P at x equal L and it just appears at the corresponding row. And this is true for arbitrary V hat, basically with the arbitrariness of V1 and V2. For any arbitrary V1 and V2, this should be true. এই অবধি বোঝা যাচ্ছে? আমার কথা শোনা যাচ্ছে?
হ্যাঁ স্যার বোঝা যাচ্ছে।
Okay. But remember, we are still in a part of a dot product. So V is taking dot product to whatever matrix. So this one is a 2 cross 2 matrix, and this one is a 2 cross 1 vector. This one is a 2 cross 1 vector, and this one is a 2 cross 1 vector, and this one is a 1 cross 2 vector. So it's a dot product that is happening. So once you take everything that is within the square brackets, then you get a vector, and you are taking the dot product with another vector. Okay. Now please understand that what this means. It means V1 times K11 U1 plus K12 U2 if Q1 minus 0 plus V2 K21 U1 K22 U2 minus if Q2 minus P equals 0. And of that, V1 and V2 arbitrary. That means you can randomly think that one of them is 0 and the other one is not. So any possible V1 and V2, this should be true. The only way this is going to be true is now whatever is multiplying V1 and V2, those are actually 0. So I'm just writing this expression first. V2 is arbitrary. So I can write K2U1 plus K22U2 minus FQ2 minus P equals 0. Okay. But now really, if you really think about the original problem, up to this it is only general. But if you think about what happened to the original problem, this one was gamma U. So V was 0. And if you map the entire geometry with a single bar element, then V1 equals 0. And that you cannot change. So V1 is not arbitrary. Okay. Which means whatever we could say about the coefficient of V2, because V2 was arbitrary, V1 we cannot say. So again, if you think about it, if you substitute V1 equals 0, so this entire term is not there. So all you have is this term, of which V2 is arbitrary, which means whatever is multiplying V2 is 0. But so we can also write it to be like something like this. But whatever is multiplying V1 is not necessarily 0. So what you get is K1 to U2, some sort of residual. We would call it R1 because it corresponds to the first row. Okay. And in the end, we would construct the K matrix multiplying U hat plus so if it is not 0, it is something, right? And that something is R1. Okay. And in the end, we have K times U hat plus, not plus, equals if Q plus 0P plus R1 0. Okay. So please understand this stiffness matrix of yours, which looks like 1 minus 1 minus 1 1 times EA divided by LE. Okay. That is not invertible because determinant of K is 0. 1 times 1 is 1, minus 1 times minus 1 times minus 1. So it is 0. So it's not invertible. So which means you can solve for U2 only when the value of U1 is given. But then you have still two equations. So it has, this one has two rows, right? 2 cross 2, 2 cross 1, 2 cross 1, 2 cross 1, and 2 cross 1. So this one has 2 rows. So the second row, of course, will let you solve for U2. But what does the first row let you solve? It lets you solve for R1. For instance, if I take the uniformly distributed load equals 0, that implies FQ equals a vector of zeros, and then you have U2 from this equation number 2 over here. U2 equals P divided by K22, which is P times LE divided by, or rather in this case it would not be LE, it would be simply L, because LE equals L because the element spans over the entire geometry, PL by EA. So U1 is fixed, then P divided by A is your stress, divided by E is your strain, multiplying the length. U2 is your total elongation. Now what happens to R1? So R1 equals K11 times 0, then minus EA divided by LE times U2, which is PL divided by EA. Then of course we have assumed Q0 to be 0, so minus 0. So in the end, R1 turns out to be minus P, which basically talks about having a reaction force R1 equals P or minus P on this side, on the left side. Okay, so if I'm showing minus P, then I should be showing that with a positive X direction. So you have a minus P acting on this side, keeping the object in equilibrium. Okay, so as it turns out that when we argued that because V1 is 0, whatever is V1 multiplying is not necessarily 0. Can it be 0? Yes, of course it can be 0. If you didn't apply any distributed load, if you didn't apply any concentrated force, it could be 0. Okay, and if you could be applying some temperature and there is thermal elongation, then U2 need not be 0. But still, your R1 would be 0 if there is no P and FQ and nothing to resist U2. Okay, so it's not necessarily 0. It can be 0, but it's not necessarily 0. And if it is not necessarily 0, it is something. And that something just turned out to be the reaction force at the boundary where the displacement boundary condition is given. এই অবধি কি বোঝা গেল কি হলো এখানে? এই পার্টটা বোঝা গেল না কি বললাম? না বোঝা গেলে বলতে হবে তো।
না স্যার একবার একটু রিপিট করে দিন না।
রিপিট কোথা থেকে? প্রথম থেকে?
না
বলছি
R1 R1 is equal to minus P ওই জায়গাটা
R1 ইকুয়াল কি করে মাইনাস পি আসছে সেটা তো ইকুয়েশনে বসালেই পেয়ে যাবে। ইফ ইউ অ্যাজিউম Q0 to be 0, okay, then if Q1 and if Q2 would be 0 and U1 is 0, so U2 is P divided by K22, okay, and then you can put the expression for K22, then you will have the value of U2. That's what we got. And then in the first equation you substitute the expression for U2. U1 is already 0, and if Q1 we have assumed to be 0, then you have R1 equals minus P, as simple as that.
ওকে
স্বর্ণব কি আছো ক্লাসে?
হ্যাঁ স্যার আছি।
তুমি কি কিছুই বুঝতে পারছো না নাকি সবটাই বুঝতে পারছো? দুটো যে কোনো ক্ষেত্রে একটু বলো।
না অ্যাকচুয়ালি স্যার কি বলুন তো, কয়েকটা জায়গা আমার একটু আমি মানে আপনার ক্লাসের সাথে আপনার যে ভিডিওগুলো আছে আমি ওটাতে একটু পিছিয়ে আছি, যার ফলে আমি মানে আপনি কি পড়াচ্ছেন সেটা ফলো করতে করতে এগোচ্ছি, কিন্তু ব্যাকে আপনার ভিডিওগুলো আমি দেখতে দেখতে এগোচ্ছি, বোঝার চেষ্টা করছি আস্তে আস্তে। মানে
তুমি
ব্যাপারটা
এখন
কি-
ভিডিওগুলো দেখছো? ভিডিওগুলো তো তোমার এখন দেখার কথা না।
না
তুমি এখনকার
ভিডিওগুলো
ক্লাসটা বুঝছো না, তুমি ভিডিওগুলো বুঝছো না সেক্ষেত্রে।
না 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 আমি সেটা বলিনি যে আমি এখন ভিডিওটা দেখছি, আমি বলছি যে আমি বাড়িতে যে পড়ছি সেটাতে অ্যাকচুয়ালি আপনার ভিডিওগুলো রিকল করছি যে স্যার আপনি কি পড়িয়েছেন আর কি মানে কোন কোন জিনিসগুলো কিভাবে ডেডিকেশনস গুলো করেছেন, কারণ আমি স্যার ধীরে ধীরে এগোচ্ছি, কারণ স্যার আমার একটু ধরতে প্রবলেম হচ্ছে, তো এবার যার ফলে আমি ধীরে ধীরে একটু এগোচ্ছি স্যার। তো যার ফলে আপনি ক্লাসগুলো আপনি প্রত্যেক দিনই করেছেন, আমি বুঝতে পারছি যে আপনি কি কি করছেন, কি প্রসিডিউর ফলো করে করে করছেন, বাট আমি একটু ভিডিওতে একটু পেছনে আছি, সো যার ফলে আমার ধরতে একটু স্যার টাইম লাগবে, মানে আপনাকে ক্যাচ আপ।
বুঝতে পারছি। এবার তো আমার আমার পক্ষে তাহলে কখনোই আহ, মানে ট্র্যাক করা সম্ভব হবে না যে তোমরা একটা গিভেন ক্লাসে কিছু বুঝতে পারছো কিনা। তাহলে এটা তোমার কবে মেকআপ হবে? তোমার যেটা তুমি বলছো যে তুমি ব্যাকলগ ক্লিয়ার করছো, সেটা তোমার কবে মেকআপ হবে? বাই নেক্সট মানডে ক্লিয়ার হয়ে যাবে?
স্যার আমি চেষ্টা করছি, ওকে, মোটামুটি আর 2 উইক দিন আমাকে আমার হয়ে যাবে।
দুটো উইকই তো ক্লাস হলো, দুটো না তিনটে উইকই তো ক্লাস হলো। এনিওয়েজ, আমি ধরে নিচ্ছি এই পার্টটা তোমরা এখন বুঝেছো অথবা পরে বুঝে নেবে ভিডিও দেখে। তো নাও নাও we would do so I'll clear this and I'll give you your first assignment, first major assignment of the day. So that would be take L equals 1 meter, A equals 10 to the power minus 4 meters squared, E equals 200 GPa, and P equals 100 Newton, Q0 equals 100 Newton per meter. Solve using linear or so-called lower order bar element for tip deflection. Single bar element, tip deflection, and compare with closed form solution. Okay, now we would move to quadratic or higher order bar element. So we know that for a bar element with linear shape functions, we need two nodes. So for quadratic shape functions, we would be requiring three nodes. So for a given bar element, let's say element number 1, you would have three nodes, and your x values are, let's say, x1, x2, x3. That is a physical coordinate, and the natural coordinate goes -1, 0, and 1. And then you have your u values, u1, u2, u3, variation, of course, v1, v2, v3, and you would be having three shape functions. So n1 goes 1, 0, 0, n2 goes 0, 1, 0, and n3 goes 0, 0, 1, forming the three-dimensional identity matrix. Now, of course, ni xi j equals delta ij. That condition is satisfied. Also, ni, some ni should be equal to 1. And ni's are all Lagrange polynomial. Okay. So that means n1 equals 1 times xi minus xi2 times xi minus xi3 divided by xi1 minus xi2, xi1 minus xi3, then another term. So if you take 3 points, there would be two terms. If you take 2 points, there would be a single term. Then, sorry. There would be three terms. Sorry, if you take 3 points, there would be three terms. So the next one is 0 times, you would substitute for xi2. So xi minus xi1, xi minus xi3 divided by xi2 minus xi1, xi2 minus xi3, and then last one is 0 times xi minus xi1, xi minus xi2. So I'm substituting for the value at xi3, xi3 minus xi1, xi3 minus xi2. Now, can you solve this and give me the expression for n1?
Yes. Yes.
Yeah, can you tell me what is the expression for n1?
Sir, 1 minute.
Huh?
Sir, 1 minute.
Okay.
That the expression is xi into xi minus 1 divided by 2.
Yes. So it's like minus xi, 1 minus xi, because xi is less than equals 1, divided by 2. Would you agree to that?
Yes.
Okay. So you can do the same process, this Lagrangian polynomial formulation. Only thing is when you go to n2, this term would be 0, this term would be 1, and this term would be 0. When you go to n3, this term would be 0, this term would be 0, and this term would be 1. Okay. You can work that way, but the only reason I did that exercise to show you that these are Lagrange polynomials. The simplest way to think about it is that n1 is supposed to be 0 at when xi equals 0. So multiply xi, and n1 is also supposed to be 0 when xi equals 1. So 1 minus xi. Now, what is the value of this quantity when xi equals 1 minus 1? It is minus 1 times plus 2, which will be minus 2. So divide the whole thing with minus 2. Do you get the idea?
Yes.
Okay. If you did, then can you use this simple method to get n3, which would be, of course, 0 at xi equals 0, and also 0 when xi equals minus 1. So 1 plus xi. Okay. Then divided by 2. Because otherwise at xi equals 1, it becomes 2. Okay. Try to get n2. It should be 0 at xi equals minus 1 and xi equals 1. What did you get? পড়া যাচ্ছে না? N2
So-
should be 0 at xi equals minus 1, and N2 should be 0 at xi equals 1. What two terms should you take product of to get that?
Middle term.
Arre,
Sir, gamma square minus 1 divided by no, gamma square minus 1 into.
হলো না। It should be 0 at minus xi, so 1 plus xi. It should be 0 at sorry, it should be 0 when xi equals minus 1. It should be 0 when xi equals plus 1. Okay. Now let's see what expression does it give me. 1 minus xi squared. Okay. And actually, I don't need to do any kind of modification because at xi equals 0, this essentially becomes 1. Okay. So it should not be something মানে তোমরা যেটা ট্রাই করো না সেটা হচ্ছে মনে মনে পুরোটা ভেবে নিতে। ইউ ডোন্ট ওয়ান্ট টু ডু দ্য স্টেপস করার অভ্যেসই নেই, কারণ এমসিকিউ দিয়ে এসছো, ঠিক আছে, সে গেটে হোক জয়েন্টে হোক, এবং আমার ধারণা কিছু ক্ষেত্রে মানে ইঞ্জিনিয়ারিং ক্লাসেও। তো প্রবলেম যেটা হচ্ছে there are simple steps, okay, and you simply need to follow them, and you are not habituated to do that. Okay, so you should develop a habit to deduct things and to be able to derive on your own. You don't have to give me directly the answer. I would rather appreciate if you did the steps in between and got an incorrect answer. Anyways, so these are the shape functions. The next step for us would be to write down the expression of u, which would be summation over uy ni, might as will be written as n times u hat, where n is essentially n1 n2, n3 times u1, u2, u3, and we do the same thing with v. Actually, v is not a vector, neither is u. So variation, value of the variation is essentially for us, it would be v transpose, v hat transpose, n transpose. Okay, and now it comes to x. X is also uh, mm, n1 x1 plus n2 x2 plus n3 x3. So isoparametric again. Okay, but we do a trickery, and that trickery is x2. Okay, you see, when we are dividing the geometry into elements. Okay, let's say this one is my first element and this one is the second element, and I'm spanning the geometry with two elements. Okay, now the end point, or the node on the right of element 1. Okay, let's say that is 2. Okay, and and for element 2, the node on the left is 2, so they are the same node. Okay, so kind of the location of that node is fixed, and now let's say the node number 3, which is the mid side node, need not be mid side, which is the interior node of the geometry, interior node of the element 1. Okay, and I have full freedom of wherever inside the span of 1 to 2 can I take that node to be. So similarly, there is 4 and 5. The thing is, I have full freedom to take 5 anywhere between 2 and 4. Okay, I cannot shift 2 because that is connected to two elements. I cannot shift 1 because that is one of the boundaries. So is 4. But 3 and 5, I could choose anywhere in their respective elements. And this is how I choose. I choose x2 to be x1 plus x3 by 2. Achha, this is not the correct depiction. You probably prefer it this way: 1, 2, 3, 4, 5. Okay, so I choose node number 2 to be between 1 and 3, exactly in between, and I choose that node to be the mid side node. Now, what help does it do to my formulation is that it becomes n1 plus n2 by 2 x1 plus n2 by 2 plus n3 times x3. Now, can you write down the expressions for n1 plus n2 by 2 and n2 plus n3 by 2? So you had earlier developed the expressions for n1, n2, and n3. Can you write down n1 plus n2 divided by 2? What expression do you get? বোঝা গেল কি বলছি?
হ্যাঁ স্যার,
করা যাচ্ছে?
হ্যাঁ করছি।
এটা কত দাম হয়েছে? আমি বড়টা কিনেছি, বড়টা 155 টাকা দিয়ে কিনেছি। 50%.
হলো, করা গেল? এটার ভ্যালু কত?
হ্যাঁ বলছি, x1/2 ইন্টু 1 মাইনাস জাই প্লাস x3/2।
Okay, 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 okay. Are you getting something like this?
Yes.
Okay. If you notice this carefully, these are the shape functions from the bar element with two nodes, that is linear bar element.
Hmm.
Okay. একটা জিনিস ভুললে চলবে না, that C0 plus C1 xi is a quadratic equation in xi. Is just that C2 is 0. And by that understanding, even if C1 is 0, if you just have C0, that is also a quadratic function in xi. Okay. Now, this is such a quadratic function that that which just turns out to be also a linear function. Okay. See, the being quadratic is a superset. Okay. Let's say this is the set of all quadratic functions. Okay. And this is a set of all linear functions. Then this one is a superset. This is like a 3-dimensional space. This one is like a 2-dimensional space. So by ensuring this relation between by taking away x2, the individuality of x2, by making it dependent on x1 and x3, you can make this type of a relation between x1 and x3. আচ্ছা, এইবার which basically means if I do dx dxi is just the same thing as before, which is element length divided by 2, and now it comes to getting u prime, which is also the strain, which is b times u hat, and where b is del n. So b is the matrix of individual shape function with respect to x coordinate. But then we are not comfortable with del n I del x. We are only comfortable with del n I del xi. Then multiplying with the inverse of del x del xi. So del x del xi is essentially the Jacobian J. We are going to multiply with the inverse of that, which is 2 by le del n I del xi. That implies the B matrix is 2 by le. Okay, and then we are doing del n1 del xi, del n2 del xi, del n3 del xi. Okay, এটা তাড়াতাড়ি করে ফেলতে পারবে? So what is the expression for B matrix? What is the first term? The second term, of course, is easy, right? Twice xi. So write down the expressions for ni's. For example, n1 is 1 by 2 xi plus xi squared, rather minus xi squared. Okay, so it is minus xi by 2. Sorry. So when you take derivative, it is minus half minus xi. Similarly, over here you have plus half plus xi. Okay, I believe that's what you are going to get, because in 3 is xi plus xi squared times half. Okay, একটু check করো তো whether you are getting the same set of expressions.
The same expression.
Same expressions, right?
Yes.
So let me erase everything. Now you would be looking for getting the element stiffness matrix, which is EA 0 to L, B transpose B, this time 3 cross 1, 1 cross 3, LE by 2 d xi. Of course, this goes from minus 1 to 1. Okay. Now, if you substitute the expressions for B transpose, so in the end you are going to get, I'm not going to substitute the B transpose. What you can do is, so can you tell me what expression do you get? So you can take EA, then LE divided by 2, and from B transpose you are going to get 2 by LE squared. So basically you are going to get it twice. So minus 1 to 1. Then you are going to have to take product of B transpose with B. Oh, so, LE by 2 times 2 by LE. Or if you take B to be something like, if you take B to be 1 by LE minus 1 minus 2 xi, then minus 4 xi, then 1 plus 2 xi. Can you check whether B is coming to be this expression? If you instead choose to be 1 by LE instead of 2 by LE?
Yes.
Okay, so that way it would be a little simpler. So basically here you have EA by 2 LE, and then this integration going from minus 1 to 1, and you need to multiply. You need to get each and every term of B matrix. Okay, of course it involves your even and odd functions, but don't use that principle until you multiply them. Okay, because the terms that are xi could be multiplying with another xi to give you xi squared, and term that is xi could be multiplying with another xi squared to give you xi cube, and that xi cube becomes an odd function. So that even odd principle don't apply yet. Okay, so multiply each of the term, and I'll tell you one thing: anytime you take A transpose A, then the transpose of that quantity is also A transpose A. Basically, it is symmetric. So, although we have 9 terms to determine or calculate, you can simply work with the top 6 and write symmetry. So, get the top 6 terms. Can you tell me what is the first term? Is it something like 1 plus 4 xi plus 4 xi squared? Is the first term this one? বোঝা যাচ্ছে?
স্যার 1 মাইনাস 4 জাই হবে না?
কেন হবে? ওয়ান মাইনাস হচ্ছে না?
হ্যাঁ 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 1 মাইনাস হবে।
আচ্ছা আচ্ছা আচ্ছা। It's because B1 is like 1 by LE minus 1 plus 2 xi. Plus 2 xi, na?
Yes, yes.
Okay, correct. Anyways, 1 minus 4 xi and 1 plus 4 xi would be both treated alike. And you will realize why. Because both are odd functions. Achha. Likewise, I would get probably 1 plus 1 plus
4 জাই
4 xi
প্লাস 4 জাই
plus 4 xi squared. ওকে, 6টা টার্ম দুটো হয়ে গেল। 3 নম্বর এটাও বলে দেওয়া যাবে, ইট ইজ মাইনাস 1 প্লাস 4 xi squared, তাই না? 1 3 টার্মটা।
ইয়েস ইয়েস
ওকে, বাকি 3টে টার্ম করে ফেলো। করে ফেলা যাবে তো?
ইয়েস।
This one I think is 16 xi squared.
হুম হুম
4টে হয়ে গেল। Okay. Now this could be written something like this, twice integration 0 to 1, and this time you would be dropping all the odd functions, basically everything associated with xi. Okay, so you have 1 plus 4 xi squared, 1 plus 4 xi squared, 16 xi squared. আমি এই দুটো টার্ম জানি না, but whatever that is, get rid of xi from there, and 4 xi squared minus 1. So if you do all of that, in the end you'd get some set of expression for LE, and is it 3 LE? Then 7, 16, Again 7 over here. I don't know these two terms, but this one I can figure out. It is 1. So this one is also 1. So I know 5 out of 9 terms. Okay. And now you'll see, I also know magically what are the rest of the terms. And how do I know that? It's because every times u1 equals u2 equals u3, so you need no force to create that sort of a deflection. That is a rigid body translation that we are talking about. Okay, which would mean that the net force, which is let's say if I multiply k with u and u hat and I get a vector f hat, okay, then f1 equals 0, f2 equals 0, and f3 equals 0. If the body is moving rigidly, so these forces are responsible for deflection. So since no deflection is happening, so the net force should be 0, right? Imagine if there is a spring and both ends are being moved by the same amount. What is the net force developed in the spring? It's 0, right? So here we are talking about that internal force, k times u hat. That has to be 0 when u1 equals u2 equals u3. So 7 plus 1 is 8. So I got this minus 8. Same thing here. So it is symmetric. So this one is also minus 8. Also 16 plus minus 8 plus minus 8, it should be 0. ঠিক আছে, আমার কিছু অসুবিধা নেই, অসুবিধা নেই কিছু, অসুবিধা নেই। ওকে, এই পার্টটা বোঝা যাচ্ছে তো কি বলতে চাইছি?
Yes, sir.
So the system is in equilibrium. Okay, so the net force should be 0 if all the deflections are same, which only is possible the coefficients add up to be 0. Okay, acha. So we got the stiffness matrix, and the next thing that we can do is we can figure out fq. I'll need only 2 more minutes. So fq is integration q of xi d xi. Okay, so again assume q to be q0 uniform, and then you have n transpose. Okay, and this going from -1 to 1, of course, multiplied by le by 2. So you can figure out this thing. Okay, how much is the force due to this one? And also if we assume that 3-noded quadratic shape function bar element, or the higher order bar element, if that spans from 0 to L, or the entire bar, then P times n transpose evaluated at L is P times n transpose evaluated at xi equals 1, which would again tell you it is simply 0, 0 P. So the idea here is wherever you are applying P, could it be in the middle node, could it be in the left node or the right node, there you automatically put P. Okay, so in the end your expression should be V hat transpose multiplying the element stiffness matrix that you found out, which is the total stiffness matrix now, because you have spanned the entire geometry with a single element, multiplying your u hat. Okay, remember u1 is 0, and that's why v1 is 0, but this one is true for all v2 and v3. V2 and v3 are arbitrary. So the equations corresponding to V2 and V3 would be equal to 0, and V1 not so much. So for V1 there would be a reaction force. So there you have FQ, and then you have 0p. Okay, so and that equals to 0. This again is a dot product, which basically means V1 times summation over K1j uj minus F1 FQ1 minus 0 plus V2 times summation over K2j uj, j goes from 1 to 3, minus FQ2 minus 0, and then in the end V3 times summation over K3j uj FQ3 minus P equals 0. Now V1 is 0, so this term is not there. Okay, and you cannot have the claim of that this thing goes to trivially to be 0. And since this thing doesn't trivially go to 0, then this term right here, the first row of the system of equations, okay, essentially goes to some sort of reaction force. So this equals plus this plus 1 R1. And again, you can use arbitrariness of V2. For example, V2 is 100 and V3 is 0. It's a possibility. Also a condition where V2 equals 0 and V3 equals 100 is also a possibility. So if in either condition, this expression must go to 0, that is only possible when the terms that the V2 and V3 are multiplying are zeros themselves. Okay, so again, using all the understanding that we developed in the previous example, okay, you can write down the system equations, and it would be simply K times U hat equals your FQ plus 00P plus R1 00, because the bar is being held at x equals 0, and wherever you hold something, there you have the reaction force. So remember, when you are, this matrix is not invertible, okay, only this matrix has a rank of 2. Okay, so you can only solve for U2 and U3 from this equation. Okay, Achha, this one, because this is true for any arbitrary V2 and V3, that this equations hold. So now you can only solve for U2 and U3, substituting U1 equals 0. And once you have solved for U2 and U3, you can also get R1. So the third equation is only useful in getting you R1. Okay, so there you have your final assignment of the day, which is L equals 1 meter, A equals 10 to the power minus 2 meter square, basically 1 centimeter, 10 to the power minus 4 meter square, 10 to 1 centimeter whole square. E is 200 GPa. Q0 is 100 Newton per meter, and P equals 100 Newton. Okay, you see, you have uniformly distributed load, and the quadratic bar element is supposed to give you the exact solution. So compare this one, closed form solution. That is the tip deflection, that is U3. এই অ্যাসাইনমেন্টটা বোঝা গেল?
হ্যাঁ স্যার।
Okay, so these are the only set of assignments. মোটামুটি 2-3 খানা দেয়া হলো, তো try to solve them. That's the only way you develop your understanding. ঠিক আছে, আমি পুরোটা করে দিলাম না, FQ এরটা তো আমি করেই দিলাম না, but I believe you would be able to do that using whatever we have learned earlier. Okay.
Okay.
Okay.